So welcome back to Multigrid Methods. We're in Chapter 5. This is the second of two slide decks. So the last few times we were setting up the basic building blocks of multigrid and talking about some of the basic assumptions for multigrid, including the Galerkin assumption, the approximation property, the smoothing properties, etc. And so now we want to put those into use into proving the convergence of the W cycle first, then the simple symmetric V cycle next, and then finally the generic or general symmetric V cycle last. So that's the plan for today. Hopefully I can get through these slides. If if I don't talk about other things too much, we should be able to get through that. So let's look at the W cycle convergence. So remember the W cycle was that algorithm where if we looked at the levels or a kind of level diagram, the shape of that thing looked a bit like this. So if we consider, let's say, level L equals 2, and then 1, and then 0. So the W cycle, when we're using the coarse grid correction to update our guess, I explained a level diagram, and the level diagram for the V cycle looks something like this. Okay, so two W's joined together. So this is because we're choosing in the multigrid algorithm P equals 2. All right, P equals 2. If we choose P equal 3, it looks like a more complicated W. But essentially what's happening here is after I do a smoothing step, I'm going to go use a coarse grid correction to correct my smooth approximation. And to do that, I go down to level 1. But now that I'm at level 1, I'm going to redo the algorithm all over again. So at the point of view of level 1, I do a smoothing step, and then I do a coarse grid correction to update that guy. Well, in doing so, I'm going to use 2 visits to the relative coarse grid to update finally my coarse grid correction. So once I've done that, now I exit the algorithm on level 1 and go back up to level 2. But I've only done one of the P equals 2 cycles involved in updating my smooth solution on level 2. So I go down again. And if I just track where I am on levels, then the diagram is going to look something like this for the W cycle algorithm. The W cycle algorithm is kind of close in some sense, in the way we prove it, is closest to the 2-grid algorithm. And the style of proving the convergence of it is going to be related to the 2-grid algorithm, as we shall see. But to get to the result that I want to prove, and in the details of the result, I need a couple, let's see, maybe just one technical lemma. And here it is. So for Richardson smoother, we have the following stabilities. So stability is it usually has some sort of form like this, where if I have an operator, so this is my error operator for smoothing. If I take a norm of that in the AL norm, say, when I multiply that smoothing against some arbitrary vector, if this guy disappears and going to the other side, this is what's called a stability. Okay, so this guy can be this guy is stable, meaning that it's the size in that guy in terms of its norm is small or can be controlled. So this looks a lot like if I just take this at face value, I can apply some sort of right consistency to evaluate size of the norm of this vector, and I'm going to get KLAL, right, times VL. So this is just norm consistency in the usual way. So what I'm saying with stability is this guy is in this norm. This is the operator norm now uh, in the AL inner product and norm system. This is going to be an operator norm. And I guess I've lost the symbol here, KL. So all we're saying is that this guy is less than one, essentially. If I could prove that, then that's the same as this. And that's a kind of stability, knowing that the norm of the size of this operator norm is small or less than some number. That's a type of stability. So whether I would have a 2 here or 3 or some constant, this is just going to be or come from the fact that essentially I can prove a bound on the size of this guy. And in fact, here I'm going to show this less than 1. And likewise, this is a similar sort of statement that leads to a stability. So again, this operator is disappearing on this side. So this is somewhat similar. So notice I'm using the AL norm and inner product here, and I'm using just the standard Euclidean norm here, Euclidean norm and inner product. This holds for any VL whatsoever in RNL. So let's try to prove this. So to start with, we have to assume that VL is arbitrary, right? And so let's take an orthonormal basis of eigenvectors of AL. We'll call that BL as usual. An orthonormal basis of eigenvectors of AL. So if this is the standard stiffness matrix that comes out of the finite element and the finite difference system, then these are just going to be our sign modes. But here we're only assuming that AL is some symmetric positive definite matrix, and there's nothing else we're going to assume about it. Remember, here in chapter 5, we're taking a fairly generic general approach. So by the way, we're saying AL is a symmetric positive definite matrix, and we're going to orthonormalize this basis of eigenvectors with respect to the Euclidean inner product. Okay, so we have choices on how we're going to normalize these bases of eigenvectors, but we're going to choose this. They're orthogonal only with respect to this one because this may not be orthogonal to some other metric, but we're going to normalize them with respect to this as well. Okay, so then there exists a unique set of constants, alpha 1, alpha 2, up to alpha n L, such that this arbitrary vector VL can be expressed as a linear combination in that basis. So this is the standard basis representation of an arbitrary vector in a chosen basis. These constants have to be unique because all basis representations are unique. Now, for the Richardson's smoother, recall that the KL matrix, that's the error for the smoothing operation. Actually, it's the error after applying one smoothing operation. So that's something we also call the error transfer matrix in the classical general linear iterative scheme theory. This is just IL minus lambda L inverse times AL. And remember, lambda L satisfies that it is bigger than the spectral radius of AL and less than or equal to CS times rho L, the spectral radius again. And the idea here is that CS is some number, which is basically, you can think about it as 2. It's like 1, 1.5. So it's got to be bigger than 1, but we don't want it to be too big. So we can think about it as basically it's equal to 2. What's important, though, is that CS has to be independent of L. And of course, that's true for our, this is true for our This is by our assumption, and it's true for the Richardson's method applied for the standard case where we're using the stiffness matrix coming finite element method. All right, so then KLW is equal to mu L K WLK. So if this is an eigenvector for the standard stiffness matrix AL, and this is a simple transformation involving AL, then the eigenvalues mu L for KL are very simple. It's just going to be 1 minus lambda LK over capital lambda L. Okay, that's just because if I multiply this matrix times an eigenvector, then it's just going to be the eigenvector minus a constant times the lambda LK times WK. I can pull the WK out, and then what remains is just a constant, and that constant is just mu LK as I've stated here. So the lambda LK are, of course, the positive eigenvalues of the symmetric positive definite matrix AL. And now again, you can, in the back of your mind, you can think about AL as being our standard stiffness matrix from the finite element or the finite difference method. But in this case, in chapter 5 here, it's completely general. We're not fixing it to be anything in particular. So the mu LKs are the eigenvalues of KLs, of course. So now let's, because we want to show what is the size of this object here, let's take that object and square it. So we get that. And let's put in that expansion for W or VL. Okay. If we do that, so by the way, what happened going from here to here? So this is, of course, the AL norm, and it writes out as an AL inner product. And I've changed to the L inner product by bringing the AL matrix in and attaching it to one of these two sides. And okay, because AL is symmetric in the L inner product, I can attach it to either the left side or the right side. So I've chosen to attach it here to the right-hand side, but it doesn't really matter much because when I do this inner product and use the orthonormality of the eigenvectors, I get the following sum. Sum from k equals 1 to nl, and again, I'm using orthonormality. I've normalized these things in the Euclidean norm so that the norm of each one of those eigenvectors is exactly 1. So by the way, that wasn't necessarily the case whenever we were doing this, or at least the eigenvectors that we were using were not normalized in the L inner product, in the L norm. So here we are normalizing them. But in any case, I'm allowed to do this, allowed to assume this happens for any k. And so what comes out in the end, because of this orthonormality property, is these guys come out because there are, with a square, because there are two vectors VL appearing. I only get one lambda L because there's only a single matrix AL, and then I get two eigenvalues for the KL matrix, mu LK squared, because there are two instances of the KL matrix. So this is what I get when I take this this norm and square it. So now recall for Richardson smoother, we have the following property, right? Mu L, or sorry, capital lambda L is greater than the spectral radius. That means it's bigger than any of the eigenvalues. So we can say we know that 0 is, actually we know that all the eigenvalues are strictly positive. So we know that lambda L K is strictly less, let's see, I guess less than or equal to capital lambda L, right? All of them for all K. So that implies, after a quick little manipulation, because I can divide now both sides of this inequality by capital lambda L, that shows that these numbers that result by dividing by capital lambda L are all going to be less than 1, less than or equal to 1. So 1 minus that guy is going to be still less than or equal to 1. Okay. And so these numbers are going to be greater than or equal to 0 and less than or equal to 1. I can derive that just from these two inequalities here. All right, so we can show then, or we can argue that since all of these guys are less than or equal to 1, then I can remove these guys. I can just replace these by 1, right? I can say this is just less than or equal to k equals 1 to nl lambda lk alpha k squared. And this is exactly equal to this norm here, right? Squared, that norm squared. So we have exactly the result that we wanted to prove, and it results from the fact that all of the eigenvalues of the K matrix, KL matrix, are between 0 and 1. Okay, so that proves this guy. And of course, now I can take the square roots to remove the squares, and I get the stability that I wanted to prove. So that's the first stability. How does the second stability estimate go? Well, it's going to follow, I believe, from the again, this inequality that we derived here in 5. So this is this object that we want to show as less than this object. Let's see how this can be done. So again, let's use our eigenvector expansion for VL. All right, if we do that, then we get moving or using linearity KL, we can attach that KL onto this eigenvector here, and that's going to liberate an eigenvalue. Okay. Well, if you use the orthonormality involving I probably should have used two separate summations here. So just to make things clear. So maybe a J instead of K. It's not technically wrong what I've done here, but it's a little bit misleading. So let's change to J. All right. I'll just make a note for myself for later. So it's better to use two separate indices when I have two sums inside of an inner product. All right, so the orthonormality condition that I'm going to use, by the way, then will read WLK, WLJ. Okay, on level L. And of course, that's just going to be the Kronecker delta dKJ, which is equal to 1 if K and J are equal to each other, and it's 0 otherwise. So that's what produces ultimately this this sum that I have here. And again, we're going to use the fact that mu LK is a positive number, which is less than or equal to 1. And so that was 5, and that gives rise to this. And this is just equal to the inner product of VL with itself. So that's the second stability that I wanted to show. So let's go back and recap the two stabilities that we have. This one, which is related to that stability, or it's actually this one would imply that one. And then this one, which is another type of stability where this K operator drops out. Okay, so the proof of the convergence of the W cycle uses a technique called a perturbation argument. Basically, we're going to show that the error is equal to the error in the two-grid method plus a perturbation that we're going to try to control. We're going to there'll be two contributions to the error. One is going to be just the two-grid error, and then the other error is going to be the error associated with doing the full V cycle or full W cycle, and that's what we need to control in the perturbation. Now we know that the two-grid error can already be made as small as we please because we already have the two-grid convergence proved in this section. We did it here. We revisited it and did it here. And so now we want to expand upon this. Suppose that P is greater than or equal to 2. That's what's giving us the W cycle. The traditional W cycle is just P equals 2, but generically we call anything with p greater than or equal to 2 the W cycle. Suppose that M1 is equal to M, and that's greater than or equal to 1. And this is going to be a one-sided method, so we're just going to set M2 equals to 0. And this helps because we know that the two-grid method, the one-sided two-grid method, is already convergent. So this fits into the style of that perfectly. Suppose further that assumptions A0 and A3 hold. So assumption A0 was the strong Galerkin condition. I should probably say that this is the strong Galerkin condition. Because we also had a weak Galerkin condition, actually A1 and A2. So this is the easiest. This is just A0. So A3 is the strong approximation property holding. And the smoothing we're going to assume is done by Richardson smoother so that we can use those last two lemmas that we just proved. Okay. Or we can use the two results in that last lemma that we just proved. Then for any gamma less than 1, M can be chosen large enough so that the error in solving, so this is considered the true solution here on a generic level L. If I want to solve this guy, then the error is going to be the difference between the exact solution of that and then one iterate of the W cycle algorithm. That's our multigrid with P equals 2 or greater, where we use some initial guess to start things off. Okay, so this is the error after one step of applying that multigrid algorithm on a generic level L. And notice we're solving this generic equation here. AL ULE, this is the exact solution of that, equals GL. This is less than or equal to lambda, any lambda that I want, and it can be made as small enough to obtain that, sorry, not lambda, but gamma, times the initial error, the error between the exact solution and whatever initial guess we want to throw in there. So this is saying that we're contracting the size of the error. Okay, so this is a convergence theorem. We're contracting the size of the error. This guy, importantly here, gamma is independent of this number L. Okay, this gamma is independent of this number L, this level number L. So how do we do this? So as I said, we're going to use the fact that the error on a generic level can be broken up into two pieces, one which is the two grid error and one which is a perturbation error that which is going to be new and needs controlling. All right, so the cases L equals 0 and L equals 1 are true. 1 is true clearly because L equals 0 is just that case where we use the inverse as our multigrid operator. So our iterative method is just an exact solution. There's nothing to show. The error there is going to be 0, so of course the error is contracted. And L equals 1 is also a trivial case because that's just the two-grid algorithm. It's exactly the two-grid algorithm. So in that case, we've already shown the convergence of it in this section here. So that case is done. So the proof is going to proceed by induction. The base cases are already taken care of. And now we only need to assume an induction hypothesis and show that that holds at the next level. So the induction hypothesis is going to be that EL, WL, measured in the AL minus 1, sorry, I should have said EL minus 1, WL minus 1, measured in the AL minus 1 norm is less than gamma times WL minus 1 measured in the AL norm. Okay, so this is showing the contraction in the energy norm, by an amount gamma, and we're going to assume that this is true for any WL minus 1. That's our induction hypothesis. Now we need to go into our induction argument. Okay, so let's look at the general case. Suppose that QL minus 1, 1E, RL minus 1, 1, are vectors in R and L minus 1 that satisfy the following equation. So this is what we saw. This is the problem we try to solve on the coarse grid whenever we're doing a coarse grid correction. So this guy here is the residual that we obtain on, well, it's the residual we obtain on the finer level, L, and then we restrict it down to the coarse level using our restriction operator. This guy here, QL minus 1E or 1E, is the exact coarse grid correction that we would get by doing an inversion. You can see if we just did an inversion on level L minus 1, we would obtain QL minus 1, 1E is equal to AL minus 1 inverse times RL minus 1, 1. All right, but we're not going to do that. That's if we were doing the two-grid algorithm, and let's say little l was equal to 1. Well, that would be the two-grid algorithm, but what we're really going to do is something a bit different whenever we solve this with multigrid, or we try to update this with multigrid. Remember, we said the important thing about multigrid is that this is not the exact, or the thing that we actually compute and call the coarse grid correction is no longer the exact coarse grid correction. All right, so let's try to decompose this exact solution or this exact version of the error into something which has this component in it somehow. Okay, so whenever we apply multigrid, remember we had three steps. We had the pre-smoothing, coarse grid correction, and post-smoothing. Remember now post-smoothing is gone because we're not doing a post-smoothing step. So actually our multigrid algorithm ends with this iterate UL parentheses 2. So we start with UL parentheses 0, the initial guess, and then we end with this guy. This is the thing that's coming out after coarse grid correction. What was coarse grid correction? Well, what we did with coarse grid correction was that was the solution after smoothing. We take the prolongation operator and we push that coarse grid correction up to the fine grid, and then we add it on to the smooth solution. This is the corrected solution that we called UL2. Now, of course, we're subtracting that here. And so if we subtract that, of course, we have to keep track of that by this minus sign outside these parentheses. Now here, this is the coarse grid correction that we actually generate with our multigrid algorithm. And this is the exact coarse grid correction that we would have generated by doing this step instead. So what I'm going to do is I'm simply going to add and subtract that guy. So let's add it inside of this multiplication here. So add and subtract, and what I get is this guy, and what I had previously was this. So this is the new part of the error that I have. All right, so and the signs all make sense, and that's because, let's see, if I, in here, inside of this, I add and subtract the QL minus 1, 1E, I'm going to get one with a plus sign, one with a minus sign. The first one I'm going to take is the minus sign, so the one that has to come out first whenever I add it back is the plus sign, so that's why I get the plus sign here. And of course, this guy appeared with a minus sign, and it comes back with a minus sign. So everything is kosher there. So the new part of the error is this guy. Well, I've modified it, and this part here, I've modified this in a way that this should be familiar, because if I really do use the exact coarse grid correction, then this whole update that I get here is exactly the update from the two grid algorithm. So this error here is the error in the two grid. So let's highlight that. That's the error in the two grid algorithm. So that's something that we already know. But what about this guy? This is a new thing that we have to try and control. This is something that's brand new for us. We have to figure out how to control the size of this error. But notice that this has a prolongation operator in front of it. So this operation takes part on the coarse grid. And I do this difference on the coarse grid, and then I push it back up to the fine grid, and then finally add it onto this. So these are two components of a new error. But this error is something that I can control because of the work that I did in this section here. Now, let's suppose out of the blue that M satisfies this requirement. M is going to be chosen large enough so that, remember here, P is some number which is greater than or equal to 2. And I need that because if the gamma, I'm choosing gamma to be some number which is small. It's kind of it's a priori chosen and arbitrarily small. I should also say that it's greater than 0, strictly greater than 0, strictly less than 1. Now I need to have P greater than or equal to 2 because this number, if P was equal to 1, would be 0 on the bottom. Now, what is it if P is greater than or equal to 2? Well, this number here is greater than this guy. So this number here is positive on the bottom. That's good. Now C3 and C5 are the constants that come to us from the approximation property and the smoothing property. The smoothing property is satisfied by the Richardson smoother, which is what I'm using in this case. So now let's ask ourselves, can this number M, which is a natural number, really be bigger than this number here? And the answer is yes. So these numbers here are small. They're not too large. There's something like 1 and 2. So the product is just 2. It might be as much as, the product might be as much as 10. But in any case, whenever I square that, it gets as large as, let's say, 100. What about this number here? This number here on the bottom is a positive number. Okay, so when I divide that guy, let's see, this guy on the bottom is going to be a number which is going to be fairly small. This number is less than 1 already, and this number is less than that one. So this is going to be some fraction. It's going to be like a half. And so when I divide by a half, of course, that's like multiplying this guy by 2. So let's suppose that this number on the top is, say, I don't know, 5, and this number is 1/2 on the bottom. So the whole thing is like 5 times 2. If I square that, then this number becomes 100. So I can definitely make M bigger than 100. It's not necessarily a great thing if M is super large, because that's the number of smoothing steps that I'm going to do in my algorithm, and that could be fairly expensive. But in any case, I can take that as large as I need to take it. So now where is this coming from? This is coming from the fact that I'm going to know that I need M to be this large somewhere below in the algorithm. So this is, this is one of those mathematical proofs where I know that I'm going to need this later because I've already done the proof, but I'm going to simply exhibit what I need earlier, and you'll see where this is used. All right, so we've proved Richardson smoother satisfies assumption A5 in the last slide deck, so that's good. So we're going to use that in a moment. We've now decomposed the error into 2 pieces, and we're using triangle inequality on this now. Take the norm of this, that's less than the norm of this plus the norm of this by the triangle inequality. So there's our first norm piece. Notice that the norm we're using is the AL norm. That's a standard good norm, so it satisfies the triangle inequality. And so this is the norm of the error in the two grid method, and this is the norm of the new piece that we need to control. Well, the 2-grid algorithm that we proved, or whose convergence we established in this section, this first section in the second slide deck, we got a contraction of C3 C5 over square root of m. So that was our contraction factor. So for right now, let's just put that in our back pocket. We can, of course, we can make m large enough so that the two-grid algorithm by itself converges. But now it looks like we're going to have to make the m even larger to deal with this new constant here as well. So we'll get to that momentarily. But let's see. Now, the new thing here is this. So this is the new thing that we have to control. So two-grid convergence was here, and the new thing is here. So let's see, how do we control the size of this guy? Well, let's first of all, let's look at the size of this guy, this vector in this inner product, where WL minus 1 is arbitrary. And what I'm going to try to show is that I get some sort of stability property with this guy. It's not exactly stability. Stability would be if I had AL down here as well. But what I'm going to do is basically eliminate this PL minus 1. So let's see, how do you do that? Well, first of all, let's take this. This is an arbitrary vector here. PL minus 1, of course, is our prolongation operator. This is pushing a coarse grid function or vector to the fine grid and then measuring it in the AL, the fine grid stiffness matrix norm. So we're going to square that. If we square it, we get this object here. Now I'm going to change this AL inner product to an L inner product by pulling this AL out and putting it either on the right-hand side or the left-hand side in front of this long vector here. I'm going to choose the right-hand side. Now I'm going to move this prolongation operator in this L inner product to the other side. When I do that, I have to ratchet. I have to ratchet down to the lower coarser grid. This, of course, just becomes the restriction operator. So now I have restriction, fine grid, stiffness matrix times the prolongation. And of course, because I'm satisfied the Galerkin condition in the strong sense, this is just the coarse grid operator AL minus 1. So that's A0, the strong Galerkin condition. So now what have I done? I've gotten rid of any P's and R's, and I've replaced that with an AL. And so I can pull this AL out. And now I have the WL minus 1 against itself in the AL minus 1 inner product. Of course, that's WL minus 1 norm squared in the AL minus 1 norm. So that's kind of a stability because I'm losing this guy. It goes away. But I'm ratcheting down from the AL norm to the AL minus 1 norm. Now, the reason why I wanted to do that is precisely because I have a PL minus 1 here. So I can immediately reduce this error. I can get rid of this part and just look at the difference between these two vectors, but in the AL minus 1 norm instead. All right, so now in the proof of the multigrid error relation in a theorem in the last slide deck, we showed the following equality. So I'm not going to go back to do that. I'm just going to refer you back to where we basically computed this error matrix, where we proved this error matrix is the exact error in the multigrid algorithm. So in that error relation, we proved this inequality, or this equality that we needed here. The QL minus 1, this is the exact coarse grid correction, minus the coarse grid correction that we generate with the multigrid method. We showed that is EL minus 1 to the p power times the exact coarse grid correction, and further showed that that's EL minus 1 to the p power times, this is the Ritz projection operator, times the difference UL E, this is the exact solution we're looking for, times the error after the smoothing, error after smoothing. All right, and we can change that to the error or the initial error by adding in the error of the first smoothing process, okay, the pre-smoothing. And so we get this error description, EL minus 1 to the P power pi L minus 1. This is not the pi L1 tilde, pi L tilde matrix. This is something different, slightly different. This is the error matrix associated to smoothing, and this is the initial error for the algorithm. All right, so now we've reckoned this back to the initial error. This is what we want. Okay, the error between the true solution and the initializing vector in my multigrid algorithm. So now let's apply our induction hypothesis. Based on the computation that we did on the last page where we lose this operator and change to this norm. So this is our new error that we have to, or whose size we have to contend with. And that is the error that we want to measure in AL minus 1 norm. We just showed or argued by an argument that we did in the improving the error matrix or establishing the error matrix for the multigrid algorithm, namely this step. We showed that this difference is exactly equal to that. All right, so the next step is we're going to use the induction hypothesis. And the induction hypothesis says that if we have an error matrix attacking any arbitrary vector, this is just some arbitrary vector here, in the AL minus 1 norm, the induction hypothesis says that this is going to be less than gamma times the original error back, or the original vector back. Now, why do we get this gamma to the P power? Well, we get the gamma to the P power because we have P of these to apply. And so we can pick one of them off at a time. And each one of them is going to produce a gamma in a multiplicative sense. We get gamma to the P power times this piece in here. So let's see what that buys us. Since we're assuming that the Galerkin condition, assumption A holds, it follows that we can show, and this is from a previous calculation that we did as well. So I'm just going to put exercise here to show this part, that when you take the norm of this guy, it's exactly equal to this norm. This has to do with this calculation that we did just here, because the difference between those two operators is the addition of the prolongation matrix. So here's the pi L tilde is just equal to PL minus 1 times pi L minus 1. So that fact, combined with the calculation like the one we just did here, is going to establish this result. And again, all we used is the Galerkin condition to get this guy. And the Galerkin condition comes in right there. So this is a little exercise to show this. Furthermore, we can show that for pi L tilde WL in the AL norm squared, that's just equal to this by definition. We're squaring this, so we take the inner product squared. We can pull one of these guys over to the other side. It comes over with a star because we're operating in the AL inner product. But remember, if we have the strong Galerkin condition, actually that's not true. So even if it's not the strong Galerkin condition, these guys are self-adjoint with respect to this inner product. So when we pull this guy over to the other side, it appears with a star, but it's self-adjoint. So we just get the square. Now we know because of the Galerkin assumption, that square becomes a single because this is a projection matrix. The pi L tilde matrix, the Ritz projection matrix, is a projection, a bona fide projection. So the square just becomes a 1. And so we get this. Now we can apply the Cauchy-Schwarz inequality, which also holds for the AL norm inner product pairing. And so we take the norm of the first times the norm of the second. That's Cauchy-Schwarz. And this is my universal symbol for applying the Cauchy-Schwarz, CS. So I can cancel one of those guys. And so now I have this stability, which I guess I could have established as a lemma, but let's just put that in our pocket as well. So now what we're going to do is we're going to change this object to this object and then use that stability that it just proved here. Now, the reason why I'm doing that is because this object appears with that norm. So we're going to change that to this, then use the stability. And so for this whole thing, we can show that this is what we established previously by the induction hypothesis. Now we're going to use those two little calculations. We're going to change this to pi L tilde in AL. And then we're going to use the stability 8 that we just proved. That gets rid of that guy. Stabilities, those things disappear. That's what stability means. All right, so that's the stability that we just proved. And now we proved in a lemma that this guy was stable in the AL norm. Okay, so that was, probably should have numbered that, but that's the stability lemma that we had previously. So maybe I want to give this a more descriptive name. That's from my stability lemma. Okay, so now that is a control of the size of my perturbation. Remember, I said this is going to be a perturbation argument where we split the error into two pieces. One was the two grid error and one was this perturbation error. All right, so now we've got it because now we have the total error. We split it into the two grid error and this new thing. This new thing we just showed was less than gamma to the p power times the original error. Gamma to the p power original error, measured in the AL inner product. So now this is a common factor. I can pull that out using the distributive property and I get all this mess here. All right, now I can do a little bit of, let's see, next we're gonna apply 6. 6 is where we're assuming that M was large enough so that something happened. So it was this guy here. That's our 6. So if I apply 6, I'm going to leave it as it's a very simple exercise to show that if I apply 6 on M here, then I can change this whole constant into this constant. This constant is, well, they're not equal. This constant is less than or equal to this guy. All right, so now what do I have? Well, now this can be if you just do a little bit of solving, you can show that this whole constant simplifies and reduces just to gamma. Okay, so that's another little exercise for you. The whole constant reduces to gamma. So this is equality here. I'm doing nothing else except for pure algebra. Of course, you have to take the square root of this whole stuff here, and so you get a cancellation of that because of that, and then finally you'll have it. We're squaring this guy and then taking the square root of it, so we just get lambda minus lambda p. But I have a lambda. Sorry, I keep saying lambda. I apologize. Gamma to the p power. Those cancel, and I just get gamma. So that's it. That's the error that we want to establish. So the error after one step of the multigrid algorithm in the AL inner product is reduced, right? Well, I guess this error gets reduced by this amount, gamma. So gamma is some number between 0 and 1. So this says the error is contracting. This gamma is anything that we want to choose. And it's level independent. And so we get the convergence over our first multigrid algorithm, the W cycle algorithm. All right, so this is worth a cheer because this is a lot of work. This is the convergence of our first multigrid algorithm. All right, so let's make a comment. Well, the comment that I wanted to make, I've already said. Remember, we have in the basement of some factorization, we have gamma minus.
Dr. Wise,
Yeah.
There's a typo on the previous slide.
Okay.
That C3, C5 over gamma minus gamma P should be inverted, and that's how you get the gamma directly.
This guy here,
Yes, that should be inverted.
what is
Oh, I'm
inverted?
sorry, you
No,
have
there's a
negative one
negative
half.
one
My
half.
bad.
Yeah. That's a good point. So minus 1/2 means that I flip it and then take the square root. So the square goes away. C3, C5 does cancel, and I just get gamma minus gamma P plus gamma P, and it should cancel. So, all right. So now remember in the basement here of this weird parameter that I'm constructing, I need gamma minus gamma P. And that's ultimately because I need to spring forth this gamma by itself. I need the gamma to the P to cancel. So I need this to be different. And so this is saying that if I have P equals 1, this argument doesn't work. If P is equal to 1, the argument doesn't work because this guy here is going to have to be is going to be infinity, and I'm not. It's just not going to work out. Um, Another way of looking at it is if, from this point of view, if gamma minus gamma P, if P is equal to 1, this is 0, then I have to take an M which is infinitely large, right? Because I have C3 times C5 over this quantity squared. This is 0, then this is going to be an infinitely large number. And there's no way I can achieve that with a finite integer M. And so any way you look at it, this argument just breaks down completely if P is not greater than 1. So that the only way this works is for P greater than 1. So this only works for the W cycle, not for the V cycle. So how do we, so this, then there's a big question. How do we prove V cycle convergence? That's a good question. The V cycle is the P equals 1 case. So that's what we're going to get into in the next section. All right, so now we want to prove the convergence of the simple symmetric V cycle. And as I said before, this is the case where P is equal to 1 and M1 equals M2 equals some common value M. And that common value is, in this case, exactly equal to 1. This is what we call the simple symmetric V cycle. It's actually amazing that this converges because we're not taking an arbitrary number of smoothing steps. Remember, smoothing was our key to victory previously. We would always say, as long as I take a large enough number of smoothing steps, in the chapter 3, we said or argued, well, we only have to take M equals 1, 2, or 3, something like that. But here we're showing that we get convergence right away for M equals 1. So this is kind of remarkable. Okay, so we need a couple of new assumptions and even some lemmas, technical lemmas to get us started. And so these are technical and complicated, so we might not get all the way through this, but let's get started. So we say that a multigrid algorithm satisfies the second smoothing property. Remember, we've already introduced one smoothing property, and I promised we were going to introduce more. So here it is. It's called assumption A6, second smoothing property. Yeah, I'm sorry that 2 matches with 6. It's not exactly looking great, but this is the usual way for multigrid literature. They like to use their assumptions. If and only if there's some constant C6 greater than 0 such that VL in the Euclidean norm squared is less than rho L. This is going to be, rho L is of course the spectral radius for AL, the stiffness matrix on level L, times that constant C6 squared times the quantity KL bar VL VL in the L inner product. This is the Euclidean inner product. This thing is a new matrix that I'm just now going to define for you, the KL bar matrix. That guy is equal to IL minus KL star times KL times AL inverse. So remember what KL was by definition. KL was IL minus whatever you're using as a smoother, SL times AL. And KL star is IL minus SL transpose AL. So we showed way back in an earlier chapter that if I take the adjoint of this matrix, then the adjoint is precisely equal to this. So that means that if this guy equals SL, in other words, if SL is symmetric, then KL is self-adjoint. If SL is symmetric, then KL is self-adjoint. So that's precisely KL star here, multiply KL, I minus L, KL star KL times AL inverse. That's this thing called KL bar. So that's what we mean by the second smoothing property holding. Now, of course, this wouldn't make sense if it weren't for the fact that our now tried and true smoother, the Richardson smoother, will satisfy this condition. So the Richardson smoother satisfies A6, the second smoothing property, with SL equals to gamma, or sorry, capital lambda L inverse times AIL. And of course, since this is just a number times the identity matrix, it's symmetric. It's its own transpose. So here's the proof. So recall for Richardson smoother, we're choosing a parameter capital lambda L, which is bigger than the spectral radius, but less than some constant CS times rho L. Okay, so CS is some number. I like to think of CS as being like 2. It's some number greater than 1, and it should be not too large, not too much larger than 1. So this guy has to be also independent of L. Then KL bar, what does that guy look like? So for this particular, for Richardson's smoother, let's figure out what KL bar looks like. Well, by definition, it's that. And now we're going to throw in our definition of KL because we know what SL looks like. Right? SL is just equal to that. And so at the end of the day, after some algebra and exact equality here, this should be 2 lambda L, capital lambda L inverse times IL minus capital lambda L to the minus 2 power times AL. Now I'm going to define a new matrix called JL. JL is equal to rho L CS KL bar minus IL. If we can show that JL is symmetric, positive, semi-definite with respect to the Euclidean inner product, then we're immediately going to get A6 with C6 equal C6 squared equal to CS. So this is a little exercise that you can show without too much trouble. That just follows from the definition of A6 straightforwardly. So let's show that this guy is symmetric, positive, semi-definite with respect to that. And then we'll get A6 as you'll see. Well, this new matrix JL is clearly symmetric because this guy is symmetric and it's a difference of 2 symmetric matrices, right? So if I multiply constants times this guy, that's not a big deal. The difference of 2 symmetric matrices are symmetric. But the important thing here is that this guy is going to be symmetric, positive, semi-definite. Well, it's not clear that that is going to happen because I'm subtracting something from this guy, right? But let's see what happens. So let VL1 be an orthonormal basis of eigenvectors for AL normalized with respect to the Euclidean inner product. And let's just start calculating. So I'm not sure why I called these VL in this case. Probably should have used WL as usual, but I strayed a little bit. All right, so JLVLK. That this is just multiplication and using the definition. Using the definition of K bar, we have all that. There's K bar right there. And now we're just going to do some manipulations down to equality and use the distributor property to pull out this common vector because it's an eigenvector for everything is in sight. For the KL bar matrix, for AL matrix, for the IL matrix, it's an eigenvector. And when I do that, I produce all that as my eigenvalue for JL. So now I only have to set or to show that this is greater than or equal to 0. This whole thing is greater than or equal to 0. So let's call it something. Let's call it A to LK, might as well. So that's A to LK. Let's show that that's greater than or equal to 0. Well, this follows from the fact that lambda L is an essential upper bound for all of the eigenvalues. So I'll skip this. I'll skip the details of this step for the sake of brevity. But that's basically why this is happening. Um, since lambda L is bigger than rho L, and it's bigger than any of the eigenvalues that we're liberating because those are just the eigenvalues for the standard stiffness matrix, I can show at the end of the day that this A to L K is greater than 0. Okay, it's greater than or equal to 0. All right, that's good because I wanted to show that this L matrix was symmetric, positive, semi-definite. So now let's show that this is really just A6. So if I put in JL in this inner product here, right? So I just showed that all of it, I showed it's a symmetric matrix and all of its eigenvalues are greater than or equal to 0. So that's the definition of SPD, right? Showing that the eigenvalues are all greater than or equal to 0. That was something that we showed followed from that definition and give us an equivalent statement. But this is what was the original definition of what it means to be symmetric, positive, semi-definite. But if I put in the definition of JL, that's just this times that. Now, if I move this guy to the other side, voila, that becomes property A6. If I move this guy to the other side because it has a minus sign here, that becomes property A6. But remember, I wanted a C6 squared here. Well, I'm getting or liberating the CS. So that just means that C6 squared is our CS. And that proves the result. So that's the first technical lemma that we need, that the Richardson smoother satisfies the second smoothing property A6. We're going to use that in the proof of the convergence for our simple symmetric V cycle. All right, and we need a couple more technical lemmas. So I imagine we'll just get through the technical lemmas and then finally the statement of the theorem, and then we'll pick up with a proof of the statement of the theorem next time. All right, but let's get to these two technical lemmas. Let JL be any matrix in RNL and L such that it's self-adjoint. Then we can show that JL, VL, JL, VL in the AL inner product minus JL squared, VL, JL squared, VL in the AL inner product is less than or equal to this quantity. This is a kind of ratcheting property. So you see, I have a J and a J, JL, JL, and JL squared. And so I can reduce the order of this guy by 1 and reduce the order of these guys by 1 and get something which is still larger. Okay, so notice this is the same as this, but I've lost a J and lost a J. And this guy here is the same as that, except that I'm going from JL squared to JL and JL. So this is kind of a stability. This is kind of a stability property. Stability property for me is anything where we kind of lose an operator in going from the left-hand side to the right-hand side. Now, more traditionally, stability is something like, okay, we say that B is stable if and only if I get a constant times WL. That's what a stability looks like. We say B is stable if this holds for some constant for any WL. Okay, as long as the constant is independent of WL. So in this case, it's another type of stability if this holds whenever C is equal to 1. Okay, so this is a type of stability for me if I'm looking at it. So I'll just call it that. But more traditionally, this thing I'm about to delete is what is commonly called a stability. Let's prove it. All right, so since A is SPD, then it holds that, um, you know, this is, of course, a bona fide norm. So norm of anything squared is going to be greater than or equal to 0. Let's use the definition of what that norm is squared. Of course, since we're working in the energy norm, we just get an energy inner product. Now, so we started off with this guy here, IL minus JL squared. For us, in the first step, it doesn't matter what that is, but we're using the fact that that's going to be this particular matrix. And now let's FOIL that guy out. So if we FOIL that out, what do we get? Actually, sorry, we don't need to FOIL it out because there's no square here, but we will be essentially foiling in a second. IL VL, JL squared VL, and the same thing there. Now we're going to FOIL out this inner product. And so we need to take this times that, minus that times that, minus that times that, and then finally plus that guy, right? So this is foiling in the inner product. All right, but now we have greater than or equal to 0 over here. That's the important thing to notice. We get a 2 here because these two things are exactly the same, right? And so now we can move things over in a sort of judicious fashion. So what do I want to move over to this side? Well, I want to move over one of those guys, and I'm going to leave one behind. And I'm going to leave this guy over on that side. I'm going to move this guy over to that side. And so what we're left with on the right-hand side is just that, and on the left-hand side, just that. So again, this holds for any J that we want whatsoever, as long as JL is self-adjoint. Now, where did we use the self-adjointedness? So we use self-adjointedness precisely because we're operating in the AL inner product. I got these JL squared, and what I did was I moved one of them over to here and one of them over to here. I didn't have to worry about that with the other inner products because those are balanced. But with these two guys here, I had to move one of these products over. And when I did so, it gains a star, but the star goes away because the vector, or sorry, the matrix itself is already assumed to be self-adjoint. Okay, so this holds for an arbitrary J as long as J is a self-adjoint operator in the AL inner product. The next lemma that I need to establish is this one. We're not going to be able to get into the proof of it. The proof is just a single page. Actually, I'll hold off on that. I'll hold off on that. I'll state it and then we'll prove it first thing next time. So pi L minus 1 matrix, that's our Ritz projection matrix. Remember, the coarse grid Ritz projection matrix is a little bit different. That's related to that by the following definition. This is pi L tilde is PL minus 1 times the pi L matrix. All right. And this satisfies in total, this is PL minus 1 A. Let me see if I can get this correct. L minus 1 inverse R L minus 1 AL. Okay, think that's correct. In any case, we want to show that this inner product in the AL minus 1 inner product is exactly equal to VL in the AL inner product minus this projection IL minus pi L tilde. This is the coarse grid rich projection matrix, VL against VL in the same inner product. So that's what we're going to prove next time. That's a key step to proving the convergence of the V cycle. So that's this theorem here. So that's what we're going to do first thing next time. The proof is about 6 slides long, and then there's another corollary after that proof. Let's see, where's the corollary? The corollary is here. The corollary is just kind of showing why the convergence proof for this is useful or can be turned into something useful. But in any case, let's stop there. And we'll pick up with the proof of this technical lemma first next time, and then we'll get right into this theorem, which is the core of the convergence of the simple symmetric V-cycle method.